Yeah. Actually, multiple. Okay, so good morning, everyone. You guys can hear me, right? It's clear.
Yes, sir.
Okay. Okay, so let's start. So in the last lecture, I was talking about few examples of sufficiency. So what is the sufficiency? Sufficiency is simply so is sufficient for the family P if x squared given px squared is the distribution does not depend on P for all P belongs to this script P, right? So this is the definition. So T is sufficient if the conditional distribution does not depend on P. So if you do not have any question, please mute your microphone. Okay. So you were looking into few examples. So the last example that you have seen is a non-parametric example where you were given um, an IID sample from some absolutely continuous distribution. So absolutely continuous means absolutely continuous. Um, so in general, whenever we say absolute continuity, we generally mean the absolute continuity with respect to the Lebesgue method. Okay. So that means whatever continuous distributions you have seen till now, so all are absolutely continuous because those are actually not only continuous but actually absolutely continuous with respect to Lebesgue. With respect to Lebesgue. So that means you can characterize this family, the family of all absolutely continuous distribution, uh, using their PDFs. PDF with respect to the Lebesgue. So PDF is same as the derivative that you have seen in the last class. So it's the PDF probability density function of the underlying distribution. So this family is characterized by the PDFs or the family of PDFs. Okay. So here the underlying family of models is simply the family of all absolutely continuous distributions. Okay. So here we want to find some sufficient states. So first of all, always the sample is sufficient. That is trivial. So what will be another sufficient statistic apart from this sample? So the claim is that the order statistics is sufficient. Why is that? So what you need to show? You need to show that the conditional distribution of the sample given this order statistic, the collection of order statistics, that is independent of any choice of absolutely continuous distribution, right? That is what you need to show. And that is kind of obvious because for any continuous distribution, whatever continuous distribution you have seen, you know that if you are given two independent observations from the same distribution, then actually the probability that those two are equal, that is equal to 0, right? That you know. So using that fact, you can simply claim that this x1 xi is equal to xi given x order I is equal to, I should say, a particular choice. So So I should not write like this. X only. When x order n is equal to something, some how should I- okay. So let me first give you the intuition, then I will write. So if suppose this order statistic has these values z1, z2 up to zn, then what are the choices of this sample? So if this is given, then what are the choices? What are the values that this sample can take? So the sample can only take some permutation of these values, right? Nothing else. And how many permutations are there? They are in numbers, so they are in factorial permutations, right? So that's why. So what are the possible values of this? The possible values of the sample. The possible values of the sample given the order statistics taking these values is simply some permutation of this. So then there are n factorial permutations, and that's why n factorial choices of this sample. So that means each choice will have probability 1 by n factorial. So x1 is some, let me write like this, sigma 1. Sigma is simply some permutation of this 1 to n given xi, and that is simply 1 by n factorial. And the probability that xi takes any other value, that is equal to 0. I am not writing that. And why it is 1 by n factorial? Because each one has the same probability, right? Because each one has given these values taking z1 to zn, x1 to xn can take any permutation with equal probability, right? Because these are absolutely continuous, there is no distinction between two values. So that's why. So since it's independent of any choice of the absolutely continuous distribution, so that's why this choice, the collection of order statistics is sufficient, is independent of any p, right? Hence this is sufficient. So so this is a non-parametric example. So here the class is large, so that's why you need you need the large number of sufficient statistics. So if you consider large number means the dimension will be higher. So for example, in case of Bernoulli or normal, you have more precise information about the underlying distribution, and then you have seen that for those distributions, the sufficient statistics has dimension 1. But here, since you are looking into much bigger class and looking into class of all absolutely continuous distribution, here the dimension of the sufficient statistics that cannot be reduced. So here the dimension is n, here also the dimension is n. But this the order statistics is somehow reducing the sample actually, because it's ordered. It's ordered. That's what you are getting. Okay, so you will see few more examples, few more assignments also, I think, on this class. You will see
Excuse me,
later.
sir.
Yeah, sure.
Sir, here x1, x2, xn are absolutely continuous, means follows absolutely continuous distribution. So can we write probability x1 is equal to z sigma I? Means it's absolutely continuous. That's
No, whenever it's given that, whenever it's given this, then it's not. Then the values of xi. So these are those become discrete actually.
okay.
So whenever this is given, whenever these statistics are given, these order statistics are given, taking some values. So given that, so actually this xi's are actually discrete, nothing else. So
Okay,
there
sir.
are in factorial many points, right? Yeah. Okay. So actually, how you define the conditional distribution? So in the conditional distribution, conditional expectation. First, to define the conditional expectation. So if you want to go through the measure theoretic way, you first define the conditional expectation properly. So it's simply some measurable function, okay? And then you move to the conditional probability. And the conditional probability is some measurable function because it's a conditional expectation of the indicator, and also it's a measure. There are two things of conditional probability. So here we are looking into some conditional probability in all of the problems of sufficiency. So it's kind of the theory behind it, that the measure theoretic way of defining the conditional probability is kind of deep. So I'm not going into that, but how you generally define the conditional probability in using the elementary probability techniques. So you generally look into the neighborhood of those points, right? And then take the limit. So similarly, here also you can do the same thing. Whatever you are saying, you are actually right, because these x's are actually absolutely continuous. But if you define in that way, just look into the some neighborhood of these points and take the limit, you will get the same thing. It will not matter. Okay. Okay. So whatever examples you have seen till now, in these examples, I have simply used the definition, nothing else. Definition of the sufficiency. So the point is that using definition, we can only check whether some statistic is sufficient or not, right? We can only check. We cannot find a sufficient statistic, because if you want to find it, then the definition is not useful, because you have to know the what is the statistics you are aiming at, and then you need to find the conditional distribution with respect to that statistic. But so that's why the definition actually is not useful in finding some sufficient statistics, and hence comes the Neyman factorization theorem, Neyman-Fisher factorization theorem. I think the screens are right. Okay, so one thing that I want to mention is that I have uploaded few pages of note on different measure theoretic tools in the course website. So if you want, you can look into those actually. So I will also add few more things there, but for the timing, I have uploaded mainly the different classes of sets, which covers the sigma algebra, and then the measure, and then I just defined what is the measure integration, and then I went to that absolute continuity and the measure derivative. So you guys can look into those, and if you have any question, you can definitely ask. Okay. So Neyman-Fisher factorization theorem tells you that suppose we want to find a sufficient statistic T based on X curve for the model script P. So this script P is the family of models. Sometimes I will say this is the model. Model means the each individual belonging to this class is a model. So sometimes, so this is a family of model or the model. It's fine. So suppose this is the aim. Suppose we want to find the sufficient statistic P based on the sample X curve for the model split. So then, if X curve is defined on omega split F P and P composed of X curve inverse, that is the distribution of X curve is absolutely continuous with respect to some sigma finite measure nu, then okay. So then P is sufficient if the density of the distribution of X curve with respect to the sigma finite measure nu, that is equal to GP of P X curve for all P belongs to split. So this is if and only. Okay. So this is kind of, you can think of this as the alternative definition of sufficiency. So where this GP and sorry, C. So I should write, so this function G has two arguments. This is one argument, this is another argument. Okay. So I'm writing like this. Are measurable functions and G dot dot depends on X curve. So P and H is a function of X curve. So this is the Neyman-Fisher factorization theorem. So here you can simply think of this nu as the Leibniz measure. Then this P composed X curve inverse is some kind of some absolutely continuous distribution. Then, for example, you can assume normal. So then you are simply looking into the joint PDF of X curve and checking whether it can be written as the product of two functions. One function depends on the model and the statistic, and it does not depend on the observed sample explicitly, but it depends on observed sample only through the statistic T. And the other function H only depends on the observed sample X curve. Okay. So this is the definition of this is the Neyman-Fisher factorization theorem. It's simply, so you can simply think this quantity as a PDF or PMF. Okay, nothing else. So for the general proof, so if you want to prove this most general version, so actually it requires many tools from measure theory. So I will not go into that because that will be difficult to handle again. So for that, I think you can look into. So for the proofs, see section 2.6 of Lehman Romano. The book by Lehman and Romano. Okay. So for the general version, but it is you should know the general version. Why? Because you only know that till now. I think you only know that if it is PDF or PMF, that means if it is absolutely continuous with respect to Lebesgue or the absolutely continuous with respect to counting, then only the Neyman factorization theorem can be applied. But that is true. But the factorization theorem actually much more general. So you can consider any sigma finite measure. The sigma finite measure, you already know what sigma finite measure is, and the sigma finite measure is simply so the Lebesgue measure on RBR and the counting measure on the natural number, and or more generally on the integers. So those two measures are sigma finite. Okay. So obviously this case includes the PDF and PMF case. Okay, but in general, this new may be anything, not only the Lebesgue or the counting. Okay, so that's why it's more general, and it somehow also covers the mixture distributions also. Okay. Okay, so let me go to the simpler version. Simpler version is for the parametric family. So simpler version. So let X curl be defined on P and absolutely continuous, not absolutely continuous. I will just simply modify this. Or let me totally ignore this major theoretic thing. So let X curl be sample P theta. Theta belongs to script theta, which is a subset of some d-dimensional Euclidean space, d belonging to the set of natural number. Then is sufficient if okay. So this is a simpler version, which I think you have seen before. This is for the parametric family, and whenever the sample X curl has PDF or PMF, it cannot be mixture. So PDF or PMF, F theta dot under T theta. Then if you can write the joint PDF as a product of these two functions, where this G depends on theta and T, and H depends on only X curl, then this T is sufficient. Okay. Okay. So let's look into the proof of this theorem, this version. So only for let T is sufficient. Hence, if X curl given right. So let's P is sufficient, then the conditional PDF or the conditional PMF is independent of theta by the definition. So now, what is F theta x prime? So we need to prove this, right? Let's call this start. So to prove start. So F theta x current is simply F theta of x current and notation wise it's difficult to write x current. So let me write it like this x current t. So this is the PDF or let's say PMF say. So this is the PMF of x current. Okay. So I'm writing like this F theta of x current is this. Okay. So then this is the joint PDF of PMF of x current and t x current. So this is true. You need to check this. Check. So this is easier to see for the PMF, right? Because using in PMF, you can simply look into, you can simply write this F as a probability. And then you can simply write this F also as a probability, then you will see that these two things are same. Okay, but it's for the PDF, it's not so easy to check. Then also you need to go through those epsilon delta, all those things. So yeah, so if you assume for the timing that this is equal to this, then now this is nothing but this f of x current given t x current. Let me write again like this: f theta of t of tx, right? So the joint PDF of PMF is simply the conditional PDF of PMF multiplied by the marginal of t. So now this thing is already independent of theta, so that means it's simply a function of x current, and this thing is a function of tx current and theta, right? Because you are looking into the argument tx current, so it's simply g theta of tx current. So that means this star is true. So while checking this, simply think of the first example. That means when you want to find a sufficient statistic for the Bernoulli, so then you need to find the joint PMF of x1 to xn and sum of xi, right? Just think of that. So then you will see that these two things are same. Okay. So the if part means star is true. That means this is star. Then to show that if theta is false. Yes. Okay. Now if theta x current given t x current given t, now you need to go in the reverse direction, nothing else. So it's f theta x current t x current t divided by t small t, right? So now One more thing, I should write like this because otherwise it's 0. If Tx curl is not equal to T, then actually this conditional is equal to 0. That is how it's defined. Now again, whenever this Tx curl equal to T, this thing is again equal to the PMF or PDF of only X curl, right? So now you know from the Neyman-Fisher factorization theorem that this thing is product of uh, two functions.
Sir,
Yeah.
so what is the sign called? I mean, that is written in between f theta xt and tx. In the first line, yeah. In the middle of the both the both the expressions. So what is the sign called?
This one.
No, sir. This this one type of thing.
So he's saying about the
Oh,
identity
yes,
function.
okay. Sorry. So this is the indicator function. Sorry. I should have defined it properly. This is the indicator function. So I am saying that so this is equal to 0 if T capital T at the point x curl is not equal to T. Then actually this condition is equal to 0. So that's why there should be one indicator here. Indicator of Tx curl equal to T. Otherwise it's 0.
This I got it.
Okay. So this is the precise way of writing. Okay, so this is the thing, and what is this f theta t of t? So now simply think of the PMF. So if this f theta t of t is the PMF, then f theta t of t is the PMF, then it's nothing but sum of f theta x curl t x curl small x curl and t of small x curl such that you are summing over x curl such that tx curl equal to, or I can make it more precise. So this is simply the probability, right? This is the probability if it is a PMF. Then it's simply you are summing over all those x curl such that tx curl equal to t, and this is simply the PMF of x curl, right? If this is the PMF, this is the probability, and it's simply the sum over all the probabilities such that tx curl equal to t. So just think of the PMF for the time being because it's easier to understand. So then this is simply sum, and again this is the joint PMF of x curl. So again you can use the Neyman-Fisher factorization theorem. Okay, so it's Tx curl h of x curl such that t of x curl equal to. So now it's indicator of tx curl equal to t. So it's simply g theta of t h of x curl indicator of x curl is equal to t. And again this is similarly g theta t sum of x curl such that tx curl equal to t h of x curl indicator not x to indicator. Right? Fine. So since in this sum Tx square equal to T, I am simply putting this Tx square to be T. So that will come outside because there is no variable there. So and in the numerator, it's indicator Tx square is equal to T. So that's why I can put Tx square equal to T. Otherwise, it will be 0. So whenever I put Tx square equal to T, then these two things will cancel from both sides, from numerator and the denominator, and that means the things remain is independent of theta, right? There is no theta inside in this part. So similarly, if this is the PDF, then it's simply the integral. So then this sum will become integral. Okay. Actually, whenever you prove this result, the general result, using measure theoretic way, you do not actually need to worry about this sum or integral. So that's the biggest advantage of measure theory. So all this sum and integral, those are all actually one type of integral. This sum is also an integral. That in case of PDF it's integral. That integral is another integral. So all the things, the sum, integral, or all are actually some form of integral in measure theoretic way. So that's why the things are much easier to handle. But obviously you need the tools, the measure theoretic tools to prove that. So that's why I avoided. Okay, so the Neven-Fisher factorization theorem tells you that you can find some sufficient statistic by simply looking into the joint PDF or joint PM. Okay. So let's look into a few examples. So let's start with the trivial one. It's uniform 0 theta. Then what is the joint PDF? PDF of f theta of x curl at point x curl is 1 by theta to the power of n, indicator of 0 less than all the points are between 0 and theta, right? So that means it's 1 by theta to the power of n. Indicator of x order 1 is more than 0, and indicator of x order n, let me write like this, x order n less than theta, and indicator of x order 1 more than 0. Okay, so now this part is simply equal to g theta of tx curl, right? And this part is simply h of x curl. What is t of x curl? T of x curl in here is simply x order n. Hence, this here in this problem, x order n is sufficient, right? Right. So the proof is fine, right? I think it's fine. Just look into the note. I think you if there is any issue regarding the proof, I think you will understand. Okay, second one. Um, x in 1 these are all finite over solid circle of R to find sufficient statistic for the parameter R. So here the each observation or each individual sample. So this is a collective sample. This each individual sample point has dimension 2, nothing else. So the joint PDF of xi1 xi2 if x1 card, x2 card are at the point x1 card, x2 card is simply what is the PDF? So it's what is solid circle of radius r. It's, sorry, uniform over a solid circle of radius r. So if it is uniform, then again you need to consider the area, nothing else, right? It's the product of individual periods, and the indicator is simply the radius is r, so that means this xi1 square plus xi2 square is less than r square. For all I equal to 1. So this is again the indicator. So that means again r square to the power of n indicator maximum r equal to 1 n xi1 square plus xi2 square. Let's consider the square of that. Then it will be norm of that. That is less than r, right? So now this whole thing, or you can think of the whole thing actually. So this whole thing is g of r of t of x1 card, x2 card, and h of x card. Here this h of x card is assumed to be 1. So this whole thing is this gr of t x1 card, x2 card. Hence, by the Neyman-Fisher factorization theorem, this t of x1 card, x2 card, which is simply the norm, the maximum of norm of xi is sufficient. Right. Fine. Okay. Fine, right? Okay. The third one is the famous family, which is called the exponential family. So this is the definition of exponential family. So first of all, exponential family is a parametric family. not x squared here. So I should not write this actually because I am simply considering this p theta. So there is no sample here. So d of p theta by d at omega is simply a theta of so whenever you want to do inference based on a sample from this family, then actually from this family, then actually you will look into the density with respect to nu of p theta composed x inverse, right? That what you generally look into because you are interested about p theta as well as x squared. So, but for the time being, just assume that p theta composed x squared inverse is simply p theta here. So just assume that. Then the definition that this parametric family is a k-parameter exponential family with respect to some sigma finite measure. For the time being, if it is difficult to assume, difficult to think, so you can simply think that this sigma finite measure is nothing but the Lebesgue measure, and this is simply the PDF. So, for example, this p theta may be some, for example, you can think of normal again. So then this is simply the PDF of normal. And if you can write the PDF of normal in this form, then actually normal is exponential family. And then you need to check what is the value of k in case of normal. So here, this b1 theta to bk theta are called natural parameters. And this k stands for the number of natural parameters. Okay. Not the dimension, not the dimension of this script theta. So let's write for some dimension d. So this k stands for the number of natural parameters. This k is not the dimension of the actual parameter. Okay. So this is the definition of exponential family, and obviously this since the PDF or the PMF, if you think in that way, so that can be written in this product form. So obviously you can use the Neumann-Fisher factorization theorem to find the sufficient statistic, right? So that is the next goal. What is the sufficient statistic? If we have a sample from this family. Okay. So find sufficient statistic based on x squared based on IID is k parameter exponential. Okay. So then what is the joint PMF or PDF? So it's simply you need to then consider P theta composed x squared inverse d of x squared. Then it's simply, or here it's difficult to consider, right? Or let me write it xi. So if theta of it's nothing but x current at x current. So this is the PDF for the PMF if you think in that way. So and this is the derivative. These two things are same. So this is the more generalized way of writing the PDF for PMF. But you are simply looking into some form of PDF for PMF. So this thing, what is this thing? You simply look into the product, right? Because these are IID. So this is the product of G of xi, and there will be another sum. Right? So now, what is so you need to write it in the form of g theta of x current multiplied by h of x current, right? So an theta into e to the power of sum of j equal to 1 to k. There is I here. J theta sum of I equal to 1 to n phi of x. This whole thing multiplied by product of g of x. Okay. So that means this is g of theta. So these g and these g are different. G of theta of p of x current into h of x current. So where t of x current is simply here. What is t of x current? You need to look into this part. So it's simply I equal to 1 to n d1 of xi up to I equal to 1 to n dk of xi. Hence, by Neumann-Fisher theorem, this T of x current is sufficient. Right? So clear, right? So it's simply whenever you have an IID sample, it's the PDF or the PMF is simply the product, and since there are three products, it can be written in terms of this g theta of tx current to h of x current, and then check and then simply find what is this t of x current, and this t of x current is nothing but this k-dimensional vector, and hence this t of capital X current is sufficient for this k parameter exponential family. Okay. So as a byproduct, or find sufficient statistics for Bernoulli P Poisson lambda normal mu1 normal mu sigma square and so these each of this family is some parameter exponential family. So this is simply the two parameter. This is also two parameter. Rests are all one parameter exponential families. And if you can write the PDF of each of PDF or PMF of each of these distributions in terms of that k parameter form of the exponential family, then from there you can directly say what is the sufficient statistic, right? Because you already know that for any k parameter exponential family, this is the sufficient statistic. So you need to simply find what is the value of k, and that's it. And what are the forms of this d1 to dk? Okay, from the PDF and the PMF of these distributions. So just try to find this. And one more thing regarding the exponential family is that the exponential family, the support of the distribution of the exponential family does not depend on the parameter, right? That does not depend on the parameter, because if that depends on the parameter, then there will be one indicator, right? Indicator of say x more than some parameter theta, something will be there, and then actually you cannot write in that product form. So that means the exponential family, the support of any distribution belonging to the exponential family does not depend on the parameter. Okay. So, yeah. The question?
Sir, for that uniform circle, the previous example,
Yeah.
we took the hx curl equals to 1. Could we have taken it as the indicator as we did it in the just uniform theta IID sample from uniform theta? Could we do it like, could hx curl also be another indicator function?
Yeah, indicator of what?
Indicator that minimum of the norm is less than r.
Not less than, so what are the
Sorry,
things?
greater
So
than 0.
Greater than 0, right? But the norm is obviously always more than 0, so that's why it's irrelevant actually.
Okay, sir.
You can write it, yeah, obviously, but it's obviously always equal to 1 actually. And the point 0 does not really matter. Okay, so the proof of the exponential family is fine, right? Because this is one important thing in this chapter. Because if you are if you know the sufficient statistic for a k parameter exponential family, then you can find the sufficient statistics for many parametric families. So that's why it's important. And as I said, that the exponential family, the support of any distribution belonging to the exponential family does not depend on the parameter, because if the support depends on the parameter, then there will be some indicator which will involve both the sample and the parameter, and then you cannot write it as the product. So that's why the support of any distribution belonging to the exponential family does not depend on the parameter. Okay, and okay, so maybe tomorrow I'll do few more examples, because today time is up actually. So I'll do a few more examples of sufficiency, and I will show by an example that the underlying model really matters in finding sufficiency. So if you keep the parameter intact but change the model, okay, so then a particular sufficient statistic may not remain sufficient anymore. So I'll show that tomorrow by an example, and later I will consider a dependent sample. So whenever you look into some sample, then you generally think of the sample to be an IID sample, right? Whenever you are given a random sample, you think the sample points are IID. That is a general notion, but that is not actually true. Random means there may be some dependence also. So first of all, they may not be identically distributed. That means they may be independent, not identically distributed. That is one case. And another more general scenario is that the individual sample points may depend on one another. Okay. So random does not mean IID. Random means there is some randomness behind getting some observed value of the sample. That's it, nothing more. Okay. And one more thing I will show tomorrow by an example that in case of dependency, you actually need higher dimension of the sufficient statistic. The dimension of the sufficient statistic will be higher. Okay. In the same example, if you take the same example, then in case of IID, in the IID case, whatever dimension of the sufficient statistic you get, in case of dependency, that dimension will increase, and that is actually true. Why is that? Because in dependency there is more structure, there is more inside structure of this sample, and to capture the information of that, you actually need more information. You have to retain more parts of the sample, otherwise you cannot retain the whole information that is available in the sample. So that's why the dimension in case of dependency will increase, the dimension of the sufficient statistic. That I am going to show you tomorrow by an example. Okay, and now after doing these two, I will move to another characterization of sufficiency, and I will try to cover the minimal sufficiency also in the Thursday's lecture. Okay, so that's it for today. And if you have any questions, so please write it somewhere, and please ask me tomorrow. I'll be happy to answer. Okay. So any question or comment? Okay, fine. So I am going to post the first assignment today, and that will be due on next Thursday. So that means you will get 2 weeks to solve the assignment. So I will post sometime today. Okay. Okay. So that's it. Bye.